The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, a couple of announcements. First of all, the Wolf Lectures tomorrow, right here in 10250 at 4 o'clock. As also, there will be the weekly quiz, the mini celebration. But there's going to be, a week from today, celebration part 3. Yes, third celebration of learning. And remember, what we're shooting for is the smiley face. None of this. And those of you who are over here on the grade point distribution curve, I want to move you to the right. So I'll say a little bit more later in the week about what the coverage will be. I'll be available for office hours later. And I thought to try to cheer you up and remind you that, studying is not something you do only the night before the exam. You have to be studying on a regular basis. All right, so from the iconic film Ghostbusters, there's this one scene.
For a moment, pretend that I don't know anything about metallurgy, engineering, or physics, and just tell me what the hell is going on.
You never studied.
You don't want to be a character in that scene. So what are you going to do about it? You're going to study. All right, let's get down to work. Today, I'm going to take one day, and we're going to talk about organic chemistry. Now, I'm not going to pretend that after one lecture, you're going to walk out of here and know much organic chemistry. I'm going to give you, if you want to know organic chemistry, you're going to have to take 512, and many of you will. But I'm going to give you enough that it'll set up for the subsequent units on polymers and on biochemistry. So we'll know enough that we can move forward. So let's get into it. The definition of organic chemistry, it's the chemistry of compounds containing both carbon and hydrogen. There can be, of course, other elements present, but you got to have carbon and hydrogen to get yourself into orgo. And what makes carbon and hydrogen so special? We've been studying these elements through the semester, but just to be reminded, first of all, hydrogen is peculiar because it's got the lowest atomic number. It's got the lone proton and a single electron. And when hydrogen ionizes, it forms the hydrogen ion or the proton. That's all that's left. And this thing's very tiny, and it can form covalent bonds. It forms covalent bonds as primary bonds, and it can form hydrogen bonds as secondary bonds. So it's peculiar for that reason. It does not form ions. You cannot imagine something as tiny as a proton occupying a lattice site in an ionic crystal. Okay, now when it comes to carbon, carbon is also peculiar. It's smack dab in the middle of the periodic table on the second row, 4 valence electrons, which means that it's very difficult to ionize. If it wants to achieve octet stability, it's going to have to form covalent compounds. It's not going to acquire 4 electrons or lose 4 electrons. In rare, exceptional circumstances, it might, but commonly it does not. And with that intermediate average valence electron energy, it's going to be capable of all sorts of bonding. And in particular, because of its small size. Because of its small size, it's capable, with its small size and the intermediate value of average valence electron energy, and this is critical, is that it's capable of forming multiple bonds. Capable of forming multiple bonds. And this is key, as we'll see later when things try to polymerize. You form multiple bonds, and this is not common, for example, not the case if you look underneath carbon. Silicon, germanium, for example, same thing. Group 4, same kind of midstream average valence electron energy, but they're too big. Silicon and germanium do not form double and triple bonds. So the other thing is that it's capable of self-linking. self-linking. It can link to itself, form carbon chains, and also with nitrogen, oxygen, sulfur. So this gives it, and let's put up phosphorus as well. Phosphorus and sulfur. So with these kinds of links, we've already seen oxygen links. We'll see pretty soon nitrogen links and so on. There's millions of organic compounds, and today I'm just going to look at a few. I'm just going to give you some taxonomy and nomenclature, and we're going to walk through this. And here's the way to keep it straight. You know all this stuff. I'm just going to organize it in your minds for you. We've already studied the three different types of hybridization, sp, sp2, and sp3. And we've already seen that if you're going to have a double bond, you need sp2 hybridization to reserve one p orbital to make that pi second bond. And if you want to make triple bonds, you make sp hybridization, thereby reserving two p orbitals to make two pi bonds. So this is sigma, sigma plus pi, sigma plus pi plus pi. That's it. Now all we're going to do is go back and look at this in the context of hydrocarbons. So hydrocarbons is going to be now the focus here, and the hydrocarbons are the simplest of the organic compounds. So let's look at hydrocarbons. I'm going to look at their nomenclature and their properties, but the structure behind everything, the treatment, is the type of hybridization. So these consist only of hydrogen and carbon, compounds containing only hydrogen and carbon. And so I'm just going to go down that chart, and we'll go through. So the first one on the left is the alkanes. I'll look at the alkanes. And the alkanes are characterized by sp3 hybridization. And so this gives the maximum number of carbon linkages. Maximum number of carbon linkages. Why? Because you can only form single bonds. So if I can only form single bonds, every bond goes to a different atom. Whereas if I form double bonds, then I'm burning up some of the capability. Because if I use two bonds to get to one neighboring element, instead of two single bonds each to two different neighboring elements, I don't have as many linkages. So the maximum number of carbon linkages, and because they have the maximum number, we're going to borrow terminology from the last unit on solutions. What's the maximum amount of solute you can get into a solution called? It's called the saturation value, and they use that term here. These are called saturated. These are called saturated hydrocarbons because they've got the maximum number of linkages, bonds, and they're all sigma bonds. They're all sigma bonds. All of this is a consequence of the choice of sp3. I could have led you through all of this, but we're putting it up quickly here. All right, and so they have a common formula, CnH2n plus 2. CnH2n plus 2. And I think I've got some, yeah, this is taken from one of the other books. I know you got a list like this in your own book. So here they are. So this is just CnH2n plus 2, and you go down and there's the nomenclature. The meth, for historical reasons, represents n equals 1. Yeah, so here's what the hidden message is. You name them by the carbon number plus the suffix ane. So the anes, the alkanes, are all these sp3. So 1 is meth, 2 is eth, 3 is pro, and 4 is bute. And they all have historical derivations. Bute comes from butyric acid, which is the rancid acid when formed when, is the acid that's formed when butter turns rancid and so on. After you get up to n equals 4, it's just your Latin. So you just take your high school Latin, pentane, hexane, heptane, and so on. All right? And if you didn't take high school Latin, this is a great chance to learn the ordinals in Latin. So there they are. Now, I'm not going to expect you to, if I say decane, that you're supposed to slam down C10H22, but I would expect that I could say decane and I'd give you that formula and you'd be comfortable with it. What's the other thing to note here? While we've got this up on the chart, you can see that all of these are symmetric molecules and they're nonpolar. They're perfectly symmetric, nonpolar. And what happens as the molecular mass increases, the melting point increases, the boiling point increases, and the state of matter transitions from gas at room temperature to liquid at room temperature to solid at room temperature. So here's an excellent example of polarizability in action, because the only way one methane can bond to another methane is by induced dipole interaction. So the only difference between methane and icosane is that icosane is a honking big molecule, nonpolar, but very polarizable. And so as the polarizability increases, you can see the effect here. Okay, so that's good. So you get to learn your Latin orbitals. Yeah. Now, these are also termed straight chains. They can be termed straight chains, but I want you to look carefully at what's going on here. So here's a diagram. The first one on the left, you've seen methane many times. There's ethane, and then propane. And what do you notice here? Because of the sp3 hybridization, all of these angles are 109 degrees, including the carbon-carbon angles. And when the thing's really short, you get this zigzaggy nature. So because of the sp3 hybridization, you see the carbon doing this. This is carbon-carbon, and then the rest, forget. I mean, this is the backbone. All right, but if I get up to icosane, and I have about 20 of these things, forget the zigzag. From here, yeah, I know there's a little bit of fine structure, but for all intents and purposes, this is a chain, straight chain. And that's where you get the terminology from, but keep in mind that there is this zigzagging back and forth due to the sp3 hybridization. Okay? So that's the first point. The second point is that the bonds between the carbons are not fully specified. So for example, take the carbon here on the left, the sticks go to the 3 hydrogens here depicted in white, and then the 4th stick goes to the carbon. And then off of that carbon comes 3 more sticks, and all of these are 109 degree angles. All of that's specified, and nothing more. There's nothing saying that these 2 hydrogens in the back have to line up. These 2 hydrogens out front have to line up. That's all free to rotate. And so we have that degree of freedom there. And the result is that you can have something that zigzags back and forth. So for example, this is called eclipsed, because if I were to stand here, these 2 hydrogens are on a direct line. So the front hydrogen covers the back hydrogen, and it eclipses. This hydrogen out front is on the same line as the hydrogen this hydrogen on the front to your and my right is on the same line as this hydrogen to your and my left. And so if I were to look here from the end, this hydrogen eclipses, and so on. So if I get something eclipsed, I'm going to have a perfect straight line. If I have something that's staggered, it's free to zigzag, but it's free to zigzag and meander. And this is what happens. So here's 2 C17H36 molecules, and the top conformation is more or less straight. These are more or less eclipsed configurations. Whereas the lower one, you can see there's a fair bit of stagger, and as a result, the backbone can actually loop back on itself. But in both cases, we still call these straight chain. They're still straight chain because as you start at one end and go from carbon to carbon, you linearly go to the other end. It doesn't mean it's straight, like straight as an arrow. It just means there's no branches. So now I'm going to distinguish this from the other one by branching. So let's just get this up here. So we have straight chains is one case, straight chains, and the straight chains can either be staggered or eclipsed. And the closer you get to eclipsed, the closer you get to the more eclipsed, the straighter. I think you'll understand what this means. Staggered allows it to make large loops. And I'll just put here looped, straight but looped. You can use that to describe some of your friends too. All right, now, that's a Monday, it's a joke. You can wake up, wake up. All right, now we can look at another one, branched chains. Branched chains. And now this will be a major departure whether the chain is super straight or it does a lot of looping back and forth. the branch chain is in marked contrast. Now let me give you an example of the branch chain. Best to just do it. So here's the branch chain. I'm going to use butane. Butane. So you know BUT is 4. So that means 4 carbons, and A means 4 carbons, sp3 hybridized. So that's it. So now I'm going to write this. Here's butane, C, 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 C. And I'm going to write this as just a straight chain instead of doing this. I'm going to contrast. So I'm going to do 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay? So there we are. So this is, instead of writing all of this stuff, this is butane, and this is butane. But now here's the thing, 4-stick rule. 4-stick rule. Whenever you do an orgo, 4-stick rule. That means 4 sticks out of every carbon. So here's the carbon-carbon bond, so I need 3 more sticks, 1, 2, 3. And I know these are sp3 hybridized, but just in compressed notation, you can do this. And I'm not even going to write all the hydrogens. Here I'm going to write the hydrogens because it's sort of first time through and it's Monday and everybody needs a little bit of TLC. But now the TLC is gone. This is it. All right? I'm not even going to put the H's on the end. A stick coming off a carbon means there's a hydrogen here. All right? So how about this one? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And now let's count the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C4H10, butane. All right, now there's another way to write this. There's another way to write this. I could go like so. 1, 2, 3. I could put a carbon up here. This is a branch. You see, it's not on the straight line. And I'm not talking about eclipsed. I'm not talking about eclipse, because if I start at one end and go down the backbone, I get to the other end, I only hit 3. I never got to this one. But let's see, maybe this is different. So 4-stick rule. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Now let's count the hydrogens. 1, 2, 3, 5, 6, 7, 8, 9, 10. This is C4H10. But it's a different molecule. You can see with what you've already learned in 3091, this has a different dipole moment, doesn't it? It's got a different dipole moment. It's going to have a different polarizability. But it's a butane. It's a C4H10. So, this is called butane, all right? And this one over here historically was called isobutane. Isobutane. Because it was an isomer. It's an isomer. It's got the same chemical composition, but it's got a different makeup. It's got a different structural makeup. It's got a different, I'm going to use a material science-y word, different structure. It's got a different molecular structure. But the chemists going back 50 years ago didn't use these terms. They called it different constituents. So I'm going to use that as well. Different molecular structure or different constituents. And what do we mean by constituents? Now comes the colored chalk. So what we're going to do is we're going to circle the makeup of this. So at this end I've got, this is a CH3 here, correct? Here's a CH3 over here. And then in between, I've got CH2 and a CH2. Now let's go over here and diagram this one. The isobutane, I got a CH3 at the end and a CH3 at the opposite end. So far, same as the butane. But now look, there's a third CH3 here. There's a third CH3, and then there's this thing, which is a CH. You could argue it's a CH2 that got methylated, but, so I'm going to put a CH2 here that's been methylated. And I'll tell you what that means. Okay, so it's really a CH2 group that got methylated. So it's called isobutane, but you can see it's got different, so all I'm doing here is making the justification for the different constitution, different dielectric constants, and so on and so forth. And So this is where the chemists come in. They would say different constituents, and so these are isomers that have the same chemical composition and are different on the basis of their constitution. So they call these constitutional isomers. Constitutional. This is a constitutional isomer. Isobutane is a constitutional isomer. Now the last piece is nomenclature. They don't use this today because isobutane was a term that came out of the chemical industry because it looks like butane's got the same molecular weight, but it's very different. Today we use the UPAC notation. Remember this? International Union of Pure and Applied Chemistry. They're the ones when one of you discovers and stabilizes element 113 and you want to name it after da-da-da-da, you have to get past the UPAC committee. Okay, so their nomenclature committee would say, this is an alkane, but it's only 3 carbon units long. So it is not a butane, it is a propane. It is a type of propane, but it's not simple propane because there's a methyl hanging off the side. So in point of fact, this in UPAC notation, or UPAC nomenclature, forgive me, is a methyl propane. And furthermore, if you want to get really pedantic, and UPAC loves to get pedantic, is what they'll do is they'll number these starting from left to right. So this is the number 1 carbon, this is the number 2 carbon, and this is the number 3 carbon. And the methyl group is pendant on the number 2 carbon. So if we want to get really, really, really pedantic, and who wouldn't on a Monday morning, what we would do is we would call this 2-methyl propane. 2-methyl propane. So it's a propane, 3 carbon units. There's a methyl group hanging off at number 2. Now, I don't expect you to be able to do these on site, but I would like you to be appreciative of what this is, so I'll give it to you on an exam. All right, so we've got the isomers. And I think I've got some, I think I've got this. No. Okay, this is good. All right. Well, there's one other thing I want to talk about with alkanes. There's a other thing that we need to know, and that's about the radicals that form. The radical is a species with 1 or more unpaired electrons, right? Species 1 or more, can even have more, 1 or more unpaired electrons. 1 or more unpaired electrons. This is broken bond, 1 pair of electrons. You know, it's equivalent to broken bond. Okay, so this is highly reactive because this unpaired electron is going to go look for a mate. So if you take a look at CH4, so now I'm going to put the hydrogens in. So this is methane, CH4. I'm going to break this bond in the lower right corner and just have an unpaired electron. And this is called the methyl radical. The methyl radical. Very reactive. So you can see that this methyl radical could go up and stick onto the 4th strut of that number 2 carbon and thereby form the carbon-carbon bond. So that's why they call this methyl propane. So the methyl radical, and you can write it this way, H3C, with a dot indicating unpaired electron. But I want you to be literate with the way chemists will write this in various compact notations. So you might even see it written this way. Now, that doesn't mean that the unpaired electron's on a hydrogen. This is just a way of saying, you know, CH4 is methane, CH3 is methyl, and who cares? There's only one possible meaning to this, so it's all good, all right? Let's do 2 unpaired electrons. So I'm going to take 2 unpaired electrons. Again, this is out of the alkane, so I'll put a hydrogen above and below, so that would be like this one here. You see this CH2? So it's got carbon-carbon bonds on either side, but in point of fact, this is part of the zigzag. So I'm going to break bonds here and here. Right? So now I've got the possibility of putting a bond on either side, and this one here is called methylene. This is methylene. This is the methylene radical, and it's got 2 unpaired electrons, so we could write that as H2C with 2 unpaired electrons. And, you know, these are electrons. They're not just anywhere. They're sitting in an orbital, and that orbital is at 109 degrees from the other bonds. So it has to be sitting there reserved in waiting. So if I bring another carbon here, I get the carbon-carbon bond, and I start forming the zigzag. And there's one more that a common one that we'll need to know, and that's from ethane, which is C2H6, right? Let's start with ethane is C2H6, and I'm going to make a radical out of that. It'll be C2H5 like this, and to which I can add a hydroxyl, and now I'll make ethyl alcohol, and then it's party time. But so this is how you start, all right? This is the ethyl radical, starting from ethane. And that's pretty much it. That's about all I want you to really take away with the alkanes. C4H10, yeah, there you go. So there you can see to the left the zigzagging of the linear and butane and then the methyl propane. That's good. Okay, now let's go to sp2. Now we're going to look at the alkenes. So alkenes represent the alkenes. This is sp2 hybridization, and they contain, this means there's the possibility of a carbon-carbon double bond, and they're also known as unsaturated because they don't optimize. The fact that you spent two of your bonds going between two atoms instead of taking one bond to one carbon and another bond somewhere else means that you're under-maximized. So unsaturated hydrocarbons. Okay, and the formula for these is CnH2n, where obviously n is greater than 1. You can't form a carbon-carbon double bond with only one carbon. So, you know, the prototypical one we looked at was this one here. Just the C2, that's the first one, so it's going to be C2H4. So carbon-carbon double bond, there's a sigma bond here and a pi bond, and they all lie in a plane. The molecule is planar, 120 degrees here. So we'll put the hydrogens, you know already, I don't have to put the hydrogens there. That's good enough. All right, so what's this one called? This is called ethylene, historically, ethylene. But the UPAC notation is similar to this one. It's carbon number plus ene, E-N-E. So strictly speaking, this is what everybody knows, but UPAC insists, and I don't, you know, as you publish, you know, some editors are really fastidious, and they'll force you to change if you use this kind of terminology. So you're going to have to call it ethene. Or in the UK, they call it ethene, but everybody knows it as ethylene. Okay, so there it is. You only need one carbon-carbon bond. So you can have long chains where the position isn't fixed. So let's look at a couple of examples. So let's look at butene. Okay, first let me just write that down. That's good. The position of carbon-carbon is not fixed. It just has to be somewhere in the molecule, which consists only of hydrogen and carbon. So here's a couple of examples. I'll start with this one. This is going to be, so this is 1, 2, 3, 4. So that's a but something, and it's got a double bond. So that's a butene. It's all hydrocarbons. So that's butene here. But I could also, well, let's finish this. How many is this? 1, 2, 3, 4. See, I even tried to indicate the 120 degrees here. This is going to be 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. All right, so there's the butene. But there's another place I could put the carbon-carbon double bond. I could do it this way. Make a carbon-carbon single bond, move the carbon-carbon double bond over to the number 2 position. This is 1, 2, 3, 4. So this is going to be 1 butene, and this one here is going to be 1, 2. So we'll make this 2 butene. 2 butene. And let's keep counting here. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. I've proven to you, I hope by now, that I can count to 4. So this is 2 butene, all right, 2 butene. And if you go through this using the same kind of diagrammatic analysis as over here, you're going to come to the conclusion that even though these both have the same composition, which is going to be C4H8, they're both C4H8, but as you diagram them, you'll find that they have different constituents. So these, in fact, are constitutional isomers of one another. Constitutional Isomers, constitutional isomers. Yeah, that's pretty good. Oh, but there's even more. It gets even better. I want to focus on the bottom one, the 2-butene, and I'm going to write it out with a little bit more detail. So let's start with that carbon-carbon double bond. And we know the carbon-carbon double bond requires planar structures at 120 degrees from one another. So let's look at that one. And what we've got here is on the carbon, I've got on the one side, I've got a hydrogen strut, right? And on the other side, I've got a methyl. I put a methyl here and like that, okay? Or actually, okay, I'll do that. What I wanted to do to get really, okay, watch this. All right, so what I'm going to do on this side, same thing. The carbon has a hydrogen strut down here, and on the other side, you've got the methyl, okay? So that looks good. But there's another way to do this and still keep the carbon-carbon bond in the center. So I'm going to do that over here. So 1, 2, 1, 2. And in this instance, I'll put the same thing I have on the left side, H3C. So far, so good. I've got the same molecule. But now what I'm going to do, just for grins and chuckles, I'm going to put the hydrogen in the upper position and the methyl in the lower position. Now, these are not constitutional isomers. They have the same constitution, right? Carbon-carbon double bond, 2 methyl groups, 2 hydrogens. Carbon-carbon double bond, 2 methyl groups, 2 hydrogens. So they're constitutionally identical, yet these have very different properties. Can you see? I mean, the dipole moment's going to be different. Look, here's the charge is all up on the one side, and here the charge is more symmetrically straddled, which means they're going to have different melting points. They're going to have different boiling points, and they have the same chemical formula, and they have the same chemical constitution. So they're a different kind. There's some kind of isomers. What's the difference here? It's not the constitution, it's the way things are arranged in space. This is great material science. Spatial orientation is everything. And what do you call it when you're listening to some loudspeakers and a really good audio system, and you can close your eyes, and the violins are over here, and the cello is here, and you can hear the percussion way in the back. What is that called? Stereophonic sound. Stereophonic meaning you can render spatial resolution. So these are called stereoisomers. Stereoisomers. One's a stereoisomer of the other. So they're spatially distinguishable. So they have, for example, I went and looked this up. Let's give some names to this. In this case, all of the methyls are on the same side and the hydrogens are on the same side, so I can put a dividing plane here, if you like, parallel to the floor. And I'll just cut right through the center of the carbons, parallel to the floor. And so in one instance, all the methyls are on the same side, and here the methyls are on opposite sides of the double bond. So when they're on the same side, this is called cis-butene. And let's be super pedantic. It was a 2-butene. So now it's a cis-2-butene. This is terrific. Cis-2. And this is a 2-butene, but it's on opposite side. So this is called a trans-2-butene. Cis-2-butene and trans-2-butene. And I looked up, so let's see, which one do you think has tighter, which one's going to be more tighter packed? Which one's going to have the greater density? Which one's going to pack better? Cis or trans? The density here is 0.627, and the density here is 0.61. Okay, now, which one's going to have the higher boiling point? Which one's going to have the higher boiling point? Gee, that should be a no-brainer. Once you know which one's got the higher density, why does it have the higher density? Because there's more nearest neighbors, it's more tightly packed, so I would bet on the one with the higher density, and this one boils at boiling point is 3.7 degrees Celsius, and this one, the boiling point is, oh, hang on, I've got this backwards. Boiling point, this is 3.7, boiling point is 1 degree Celsius. So those are the data as they come out. So stereoisomers, spatially distinguishable. By the way, we can form multiple bonds. We can form multiple double bonds. So they're enes as well. So if we have 2 double bonds in the molecule, 2 double bonds, so we'll call that a diene. A diene. And we can have, you can keep going with the Latin, but the common ones you might find is a triene. And this will come back later when we look at polymers. So if we have 2 bonds, we will have, some of that hard luggage that you're seeing that's coming back. They got the roller boards, but instead of the fabric, now they're coming back with the really hard polymer. That's ABS, and the B is butadiene. Butadiene. So let's look at here's a pentadiene. I'll give you a pentadiene. So that's going to be 1, 2, 3, 4, 5. It's 5 carbons for starters, and I'm going to put the double bonds on the 1 and the 3 carbon. It'll be a penta. It's 5 carbons, and it's an ene because there's going to be some double bonds here, and it's a di because I'm going to put double bonds at the 1 and the 3. So 1 gets a double bond, and 3 gets a double bond. So this is a pentadiene. Okay. And then the last thing is, radicals. So here's the common radical. We'll start with ethylene, and I'm going to make an ethylene radical here. I'll break off the hydrogen at this point, and I can write that as CH2, CH. And we can't call this ethyl radical because ethyl was already used for C2H5. So we need to indicate that there's a double bond, and so this radical is known as vinyl. This is the vinyl radical. And so you could react this with chlorine, for example, in which case you'd make vinyl chloride, and then you polymerize that, and you make PVC. And we're going to see that in the next coming days. So, or you can put alcohol on there. I've already told you that. I don't need to remind you twice about that, I bet. Okay, so now, there's one other one. There's one other one that will come up if you take a lot of biochemistry, and that's the one that comes off of propene. So if you start with propene, propene's going to look like this. 1, 2, 3. So there's propene. 3, there's a double bond here, and I'm going to put 1, 2, 3, and here 1, 2, 3, 1, 2, 3. 1, 2, 3, 4. Okay. So there's this is the radical that comes from propene. So this one is derived from ethylene, and this one here is derived from propylene. So again, as in this case, we couldn't call this ethyl. We can't call this propyl because that's the one that you get from the alkane. So instead, this one is called allyl, A-L-L-Y-L. And if you take 7012, at some point, Professor Weinberg will refer to these pendant groups. He likes to pronounce this allyl. You'll hear him talk about, and the allyls are over here and here. That's what we're talking about. Okay, good. So this is C3H7 dot. Good. All right, moving right along. Now I want to turn to the alkynes. The alkynes. That's the sp hybridization. sp, and that means there's going to be at least one carbon-carbon triple bond. One carbon-carbon triple bond, so the formula there is CnH2n minus 2, and obviously N has to be greater than 1, otherwise you can't form the bond. And there's very little that I need to remember about this one. The dominant one that you'll come upon is C2H2. So according to UPAC nomenclature, the 2 carbons means it has to be eth, and these are all alkynes, so this should be ethyne. And if you ask for ethyne, nobody knows what you're talking about, although it's very correct. This is known as acetylene. is known as acetylene, which is a fuel gas for welding, cutting, torches, and so on. You got two lines. You got a big tank of acetylene. You got a big tank of oxygen. And this is used because there's enormous energy stored in this carbon-carbon double bond. And so when you combust this with the stoichiometric amount of oxygen, you can cut through steel. You can use this to make a very elaborate glassware with pure silica, making fused quartz glassware. Very, very high energy contained in here. And just to give one more example, let's look at something that's got 4 carbons in it. So it's going to have 4 carbons and a triple bond. So if it's 4, it's going to have the BUT, but, and it's going to need an ine. So this will be a butane. And depending on where we want to put the triple bond, I don't know, if you want to put a triple bond here, there's 1, 2, 3, 4. So this we could call 2-butane, and it's C4H6 if you go through the stoichiometry. Let's try it just for practice. So this carbon on the end is 1, 2, 3, 4. Look at this second carbon. It's got 1 strut bonding to the neighboring carbon and 3 struts bonding to the neighboring carbon on the right. It's saturated now. Nothing comes off of that carbon. Look at this one, 1, 2, 3, 4. Nothing comes off of this one. And then finally, 1, 2, 3. So there's 3 hydrogens here. There's 3 hydrogens here. There's your 6 hydrogens, C4H6. Okay, that's good. All right, there's one other set that I want to look at, and these are called the arenes. These are the aromatic hydrocarbons. Aromatic hydrocarbons. Aromatic hydrocarbons. Some people refer to them as arenes. Okay, and the most notable one is C6H6, which is benzene. And benzene, the molecular weight was determined long ago in the early 1800s, and it was Keckley who in 1865 dared to suggest that the formula for the chemical structure, rather, of benzene was a ring structure. So Keckley suggested a carbon ring. Up until this time, people didn't have the common understanding that carbons could link to themselves, let alone form a ring. And so now if we go through this, we will put from each of these junctions is a carbon. So we have to have 4 struts. We need hydrogens, so let's put hydrogens 1, 2, 3, 4, 5, 6. So there's the 6 hydrogens, and now each carbon needs 4 struts. So 1, 2, 3, and I'll put a double bond. That'll make 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, and now this one here. So you have an alternating structure of double bond, single bond, double bond, single bond on the carbons. Okay? So that's the way things stood until the 20th century when, on the basis of new data, it was discovered that all carbon-carbon bonds, and I don't want to make this a single bond, I'll just say all carbon-carbon bonds in benzene, C6H6, were measured to be the same length. Well, that's a problem, isn't it? That's a problem because we would expect that, we know that carbon-carbon single bond is about 1.47 angstroms, and the carbon-carbon double bond has to be shorter because it's double bond, it's tighter, so it pulls things in. So that's 1.33 angstroms. 1.33 angstroms, and the measurement here was found to be 1.39 angstroms. And 1.39 angstroms is midway between 1.47 and 1.33. So people were frustrated with this new information, and it was Linus Pauling who made sense of this for us. Pauling, who in 1931 came along and said, what if we have a mix what if we have a mix of two structures? And he said, suppose you had something that looked like so. 1, 1, 1. So here's the set of double bonds off of the ring. And what if there was a resonance with an opposite hybrid where this double bond, instead of being here, goes over to here? So now we have this. And he said if the system resonated between the structure on the left and the structure on the right, the time average value of the carbon-carbon bond length would be around 1.39 angstroms. So this is a resonant hybrid structure to account for the mix of single and double bonds, which gives rise to the current representation of benzene is simply this. So we're not saying this is single or double, it's a resonant between 1 and 2. Okay. The other thing is if all of these bonds are the same length, and that means that between the 12 o'clock position here and the 2 o'clock position, there is pi bonding. And then along this double bond, there's pi bonding. And then along this double bond, there's pi bonding. But if all of the bonds are the same length, I can't say that the pi bonds are confined to where the double bonds are indicated, because resonance indicates that it could be between adjacent. So that means that the electrons, in fact, can go all around. So resonance then means that the pi electrons are delocalized pi electrons. Delocalized pi electrons. And now here's some better drawings. That's hard to draw that. So here they are. Okay, so this is a nicer drawing of benzene. So you can see when all of these bonds are resonant, it doesn't matter whether I choose this front one as the double bond or the one next to it. They're all the same length, and so the electrons can go all around. And you can imagine if I did this with graphite and I kept going, well, if the electron can go here, then it means it can go here, which means it can go here, which means it can go everywhere, which is why graphite is an electronic conductor, because of delocalized pi bonds. Okay, this is 1,3-butadiene, double bond, single bond, double bond. Again, all the same length, and you can hybridize. This is how you start making electronically conductive polymers. You just go double bond, single bond, smear. That's it. Okay, let's jump over that. Oh, let's talk about Keckley. So he studied architecture, switched to chemistry, and then he got a job in London, and he used to fall asleep on the bus to his apartment. And one day he was sleeping on the bus, he woke up, and he'd been dreaming about carbon-forming chains in 1855, and he proposed carbon chains. And then he got a job as a professor in Belgium at the University of Kent. And one night he fell asleep at the fireplace, and he dreamt of a benzene molecule as a snake biting its tail while spinning. And that's where he got the idea of the ring molecule. All he knew was that this thing had a formula, C6H6. And for this, he was dubbed the founder of structural chemistry. So what's his formula for success? Well, he moved into chemistry from another field, but to dream, you got to get some sleep. And I'm probably talking to one of the most sleep-deprived populations on this campus. So I urge you to get some sleep, and then maybe you'll be able to dream. Hey, don't make noise. We got 2 minutes left. Nobody's going anywhere. Nobody's going anywhere. All right. So the next thing is I want to talk a little bit about octane ratings in automobiles and how we go from straight chains to chains of different length. If you're looking at combustion, the idea is you admit gasoline, which vaporizes, and then the piston comes up, and under high compression, the spark plug fires. When the spark plug fires, this causes an explosion, which then pushes the piston down, and then you've got the camshaft that takes the vertical motion and converts it to rotary motion. Now, if you're running an automobile after a certain period of time, the combustion chamber becomes so hot that just admitting the fuel, having it vaporized, before the piston has risen fully to give maximum compression, this thing could just explode. And when it explodes, it'll send the piston down, and it's out of sequence with the other pistons, and that's when you get the knocking. Sometimes when you're driving uphill, you hear this. That's the knocking going on. You need to get a tune-up or switch to higher octane gasoline. So what's going on in here? What you're doing is you're changing the chemical composition, the constitutional isomerization. And you do that in the process by which you synthesize the gasoline in the first place. So the figure of merit is called octane number, which was first instituted here in the United States. And they started with 2,2,4-trimethylpentane. It's an octane, but it's an octane that's 2,2,4, 3 methyl branches. So that means there's only 5 left. So it's a pentane with 3 methyl branches. And that's called 100. And then 0 is heptane. If you put heptane into the combustion chamber, you'll knock yourself silly. The engine will just shake and shake and shake. So gasolines have to be somewhere on that interval. So there's the, if you tested it and you had something that was trimethylpentane, 90% versus 10% heptane, you'd call it a 90% octane and so on. You can have octane numbers higher than 100, by the way. It just depends on what the repression is. And oddly enough, when you increase the octane, you make the fuel more difficult to burn because you want it to burn only on demand. Fuel that just burns whenever it wants leads to random events in the engine, and that's not good if you want to get good thrust. So oddly enough, high-octane gasoline requires more ignition than low-octane. And the additives are tetraethyl lead or ethyl alcohol. And from that, now we get E10, which is gasohol, 10% alcohol. E85 is 85% ethyl alcohol. And all of this you get by the synthesis, playing with the catalyst, temperatures, and so on to get the right mix to get good fuel and get good emissions. And you can decide amongst yourselves whether going to E85 with high levels of ethanol derived from corn, is that smart? Is that food for fuel? What's the sensible use of agriculture, algae, switchgrass, all of this stuff? I mean, it's all loaded into here. It's all loaded into here. So, yeah, with that, I think we'll adjourn. I'll see you on Wednesday.